AQA Science Physics course, and therefore Unit 1, Part 1, which is Energy Transfer by Heating. This particular tutorial is only interested in one of those particular topics, which is conduction. Right, there are three main methods of heat transfer: conduction, convection and radiation. At present we'll deal with each one separately, so as stated at the beginning, we're just going to be looking at conduction. We'll be studying convection and radiation in later tutorials, and then looking at how they can all be linked together to see how a common object like a vacuum flask actually helps keep things warm, or indeed helps keep things cold. Right, heat transfer in solids. The main thing with solids is that we need to understand that we have a structure of atoms or molecules all neatly arranged in rows. If you think back to your notes that you did and diagrams that you did on the kinetic theory of matter, then it's that diagram that we've got here. The main difference being that this is now in a long line like a rod. So what we have is a sequence of particles which normally are vibrating. They vibrate randomly, but there's no particular hot spot, so they all have a similar amount of kinetic energy, and all the particles are moving therefore by similar amounts. There's no net movement of energy from left to right or right to left, and the rod is basically in equilibrium with its surroundings. That means it's at the same temperature. So there's no heat transfer at all in that situation, but this is a sort of important diagram to get the fact that the particles are moving and vibrating around mean positions. If we apply a heat source, then something will change. So the Bunsen burner is positioned at the left hand side of the rod, and the heat therefore is being applied to that side, and the rod starts to glow. That means it's giving out visible radiation, in this case in the red spectrum, but it's also giving out a form of radiation that we can sense with our skin, which is infrared. We'll be studying more about infrared radiation and visible radiation at a later date. But what we now have is that one part of the rod is hot and one part is slightly cooler. It's best to stick with comparative terms, hotter and cooler, rather than hot and cold. What we see if we study the particles now is that the particles at the hotter end have gained kinetic energy. They're still vibrating about their mean positions, but they're now colliding more vigorously with particles next to them. That means they then collide with cooler particles next to them. This is heading rightwards. They collide with other particles next to them, and so energy is transferred by the collision of particles from left to right. Generally speaking, in solids, this is quite a slow process, and heat is not transferred well through most solids. Most solids we would actually regard as insulators, and heat transfer can be quite slow. In fact, in something like wood, the conduction process is so poor that the wood actually burns before it can conduct its heat. So in effect what we've got is heat moving from left to right, and if you're never sure about the way that the heat flows, it always flows from hot to cold. Alright, from hotter regions to colder regions, and it's basically by the collision of hotter particles with cooler particles transferring kinetic energy. Right, so if we just summarise that then, the energy is transferred by the collision of hotter high energy particles with cooler less energetic particles. This transfer of kinetic energy occurs from hotter to colder regions, and that is the process we call conduction. So if you make sure that you can at least write those 3 bullet points, you've pretty much got 3 marks. Each bullet point is worth 3 marks in a small, short, descriptive type question. Conduction in metals. The previous diagram really was conduction in solids. Metals are very good conductors, and there's one simple reason for that. The little red dots represent free electrons. Around atoms there is a cloud of electrons. In non-metals, those electrons are held, bonded to the actual atoms, and are not free to move away from their particular atom. So the only way heat can be transferred is just by atoms colliding with other atoms. In metals, there are some electrons which are free to move. That's what we call conduction electrons, and they cause metals to be good conductors of electricity, but they also allow metals to conduct heat. So when the rod is heated, not only do we have the collision of metal ions with other metal ions, atoms that have lost charge, we also have the free electrons moving. Because they're very small, they gain kinetic energy extremely quickly. They've got small mass, they actually move very quickly, and these electrons can move extraordinarily quickly from hotter regions to colder regions, and that allows the transfer of heat extremely quickly from hot to colder regions. The electrons collide with atoms in the cooler regions, so energy is transferred extremely quickly from hotter regions to cooler regions by the movement of these electrons. And as I said before, in non-metals the electrons aren't there, they're tied, bonded to their atoms, and so they're not free to move, so it can only be collisions of atoms with atoms, and that's much slower. Just a quick note, an ion is something which has a charge. So the metal ions are positive because they've lost electrons, and the electrons are actually negative ions. Alright, because they're negatively charged particles. If you read through the notes and just make sure that you're quite happy and understand the concept of this process of conduction is so much faster because the lighter electrons move very, very quickly, carrying kinetic energy with them from left, the hotter region in this diagram, to right, the cooler region. Okay, poor conductors are called insulators, and the best insulators are material that trap air, such as foams, fiberglass and feather duvets. So that's like a jacket. Now, these are gases. So far we've just looked at solids. Now we're looking at a gas, and what we find is that gases are not very good conductors. So although this topic has been called conduction, the last little part looks at why gases are not good at conducting. They're the worst form of conductors out there, and therefore they're very good insulators. In essence, what happens is, with an insulator, if you can trap little pockets of a gas, air, then because the particles are far apart, think back to the kinetic theory diagrams you drew for gases, because the particles in the gas are far apart, collisions between those particles are very few, therefore they don't transfer energy very efficiently. Collisions are what transfer the energy. Less collisions, less energy transfer, therefore less heat lost. That's it. So what we normally have is some form of matrix, which is a material that surrounds air, like a foam, bubbles, anything. We surround the air, trap it, stop it from moving, and therefore, because it's a gas, there's less energy, there's less transfer of energy by collisions, and so things still stay warm. Right, an exam question. You can effectively just read this answer yourself, but it's a typical thing. How, say for instance, does a mountaineer keep warm on Everest? The three key points to this one: the feathers trap pockets of air, 1 mark. Air is a poor conductor of heat because the particles are far apart and don't collide often, 1 mark. Thus energy is transferred slowly from the hot climate to the cooler surroundings, and the climate stays warmer. That effectively is the answer for 3 marks. What you would find, of course, is if you stood still long enough, eventually, without generating any internal energy yourself, even with a nice duvet jacket, you would eventually cool. So you have to keep moving. Alright? These things are not perfect insulators, there's no such thing, they just reduce the energy transfer. That's the end of this tutorial. We'll be looking at convection and radiation in later tutorials, and then putting them all together and seeing a further use. Thank you.